In nodal analysis, we identified independent nodes and wrote KCL at those nodes using Ohm's law to write KCL in terms of the node voltages. In mesh analysis, the unknowns are mesh currents. We perform KVL around mesh loops and use Ohm's law to write KVL in terms of those mesh currents. In this video, I'll talk about identifying unknowns in mesh analysis. First, I'll give a brief summary of the steps involved in mesh analysis. The first step, as with nodal analysis, is to define unknowns. To do this, we choose mesh loops. These are the loops around which we'll apply KVL later. The unknowns in mesh analysis are called the mesh currents. The mesh currents traverse the mesh loops. The mesh currents are not actual currents in the circuit, but the mesh currents can be used to determine the actual physical currents in the circuit. Then we apply KVL around each of the mesh loops. Ohm's law is used to write KVL in terms of the mesh currents. This will result in the same number of equations as there are mesh currents. The equations can be solved to determine the mesh currents. The mesh currents can be used to determine whatever voltage or current in the circuit you actually want to know. Nodal and mesh analysis are duals of one another. Roughly speaking, this means that they have similarities but within an opposite framework. In nodal analysis, we define independent nodes and our unknowns are the voltages at these nodes. In mesh analysis, we define mesh loops and the unknowns are currents going around those loops. In nodal analysis, Kirchhoff's current law is applied at the independent nodes, while in mesh analysis, Kirchhoff's voltage law is applied around the mesh loops. Finally, nodal and mesh analysis both employ Ohm's law, but nodal analysis uses it to write currents in terms of node voltages, while mesh analysis uses Ohm's law to write the voltages in terms of the mesh currents. Mesh analysis relies both on the mesh currents, which are our unknowns, and constrained loops, which account for known currents provided by current sources. I'll use this example circuit to explain how to choose mesh and constrained loops. First, keep in mind that the actual current through any element is the algebraic sum of the mesh and constrained currents passing through that element. The mesh currents are our unknowns. They're used to find the currents through the resistors and the voltage sources. We know the current through any current source, so we don't need to define those currents as unknowns. These currents are most easily accounted for by constrained loops. The rest of this video will provide details on how to choose the mesh and constrained currents. Probably the easiest way to choose mesh loops is to kill the sources. To kill a voltage source, replace it with a short circuit, and to kill a current source, replace it with an open circuit. So my example circuit becomes this. After you've killed the sources, identify any resulting enclosed, non-overlapping areas. In this circuit, one of those will be over here and one will be here. The mesh currents go around the perimeters of those areas. I'll always choose my mesh currents as going clockwise, but you can choose either direction if you're consistent about your sign conventions. If you choose mesh loops according to the rules in the previous slide, none of those loops will pass through current sources. Remember that the actual current through any element is the sum of the loop currents passing through that element. So we need to define additional loop currents to account for the current through the current sources. These additional currents are called constrained currents, since their values and directions are constrained by the current sources. The choice of constrained loops is somewhat arbitrary. The only requirement is that they form a loop so that they start and end at the same node, and that they match the magnitude and direction of the current source they're accounting for. So this is a valid constrained loop. It's going in this direction up here, which is the same direction as the 2 amp source, and its magnitude matches the 2 amp source. Likewise, this loop goes in this direction and it matches the magnitude. This is another legitimate loop, as is this one. They're all going this direction when they pass through the current source. They end up at their starting point and they have the same magnitude. Finally, I'll summarize the choice of mesh and constrained loops for mesh analysis. This process corresponds to the process of choosing independent and dependent voltages in nodal analysis. and has the same level of importance. If you don't choose your mesh and constrained loops appropriately, any equations you write to describe the circuit will be incorrect. The unknown variables in mesh analysis are the mesh currents. The best way to define mesh currents is to kill the sources. Short the voltage sources and open circuit the current sources, and then identify any remaining enclosed non-overlapping areas. The mesh currents will go around the perimeters of these areas. Using this approach to define mesh currents means that none of your mesh currents will pass through current sources. To account for those currents, define constrained loops. The path of the constrained loops is arbitrary, but they must be set up to account for the currents through any current sources in the circuit. That's my preferred approach for defining mesh and constrained loops. In the next video, I'll talk about writing the equations governing mesh currents and using the mesh currents to determine physical values in the circuit.